Ships, navigators, and airplane pilots are just two of the many professionals that use trigonometry to chart their course of flights around the globe. Hi, my name is Tom Atwater, and in today's lesson, we'll use trigonometry to solve real-world application problems. We need to start by looking at some definitions. We need to know what the angle of elevation means, and that is the angle through which the eye moves up from a horizontal to look at something. So here's the horizontal, the eye has to look up like this. There's my angle of elevation. Similarly, we need to look at something called the angle of depression. And this is the angle through which the eye moves down from the horizontal to look at something below. So in this case, here's the horizontal, and the eye has to go down, and this would be the angle of depression. Well, let's work an example where we use these concepts. From the top of the 100-foot tall Altgeld Hall, a man observes a car moving towards the building. If the angle of depression of the car changes from 22 degrees to 46 degrees during the period of observation, how far does the car travel? With many problems like this, where we will end up using trigonometry, a diagram is very helpful. So let's take a look at the diagram for this problem. Here we have the man who you can't really see, but he's up at the top of the hall. And the car is moving towards the building. So initially, he has to look down at an angle of 22 degrees to sight the car. The car moves forward a distance of x, and then he needs to look down at an angle of 46 degrees in order to see the car. And we know that the building is 100 feet tall, and by certain relationships, we can say this. We have this angle is 22 degrees, and we can also say that this angle is 22 degrees because that's two parallel lines that are being cut by a transversal, and those are alternating interior angles. And that's the same reasoning why we can say that this is 46 degrees. Now, from this, we can come up with two specific equations. We can conclude in this smaller triangle here that the tangent of 46 degrees is equal to the side opposite, which is 100, divided by the side adjacent, which is labeled as D. From the larger triangle, the one that involves the 22-degree angle of depression, what we can say is that the tangent of 22 degrees is equal to 100, which is the side opposite, divided by the side adjacent, which is the sum of x plus d. All right, well, we're going to take those two equations, and we are going to solve for our unknowns. So I've rewritten them here. The first thing we're going to do is in the top equation say, well, that means that D would be equal to 100 over the tangent of 46 degrees. Let's take the second equation and isolate x. So actually what I'll do is say that x plus D is going to be equal to 100 over the tangent of 22. And therefore, doing a simple manipulation here, I would subtract D from both sides, and I would get this equation. And what I will then do is substitute the D from the first equation, and so I get x equals 100 over the tangent of 22 degrees minus 100 over the tangent of 46 degrees. And of course, you plug that into the calculator, work it out, and it's going to be approximately 150 and 9/10 feet. So depending on how exact you're required to be, you could say it's approximately 151 feet. Let's work another example where we use these same concepts. The angle of elevation from an observer to the bottom edge of the Delaware River Drawbridge observation deck located 200 feet from the observer is 30 degrees. The angle of elevation from the observer to the top of the observation deck is 40 degrees. What is the height of the observation deck? Well, once again, we're going to start this problem by looking at a diagram of what's going on. So you can see this time we have the observer, and when he looks at the bottom part of the deck, it's a 30-degree angle. And when he looks at the top portion of the deck, he sees, or he has to look up at a 40-degree angle right here. We know that he's 200 feet from the tower. Well, in this case, let's label a little bit more information. Let's take the smaller triangle, and we will call that X. And that's going to be this side right here. Okay. Then we have the larger triangle, which I will refer to as being equal to A. The whole thing is A. All right, because now we can set up the fact that the tangent of 40 degrees is equal to the side opposite, which is A, over 200. And then my other problem would be the tangent of 30 degrees is equal to X over 200. So once again, we'll take those two equations and use them to solve for the height X, which is, we're going to solve for A and X, and what we're going to come up with eventually is the height of the observation deck. So first we need to calculate this information. So we had tangent of 40 degrees is equal to A over 200. And that means that A is equal to 200 times the tangent of 40 degrees. So that means, plugging it into the calculator, we'll find that A is equal to 167.82 feet. The other equation we had was tangent 30 degrees was equal to X over 200. That means X is equal to 200 times the tangent of 30 degrees. Plugging that into the calculator, we'll find that X is equal to 115 and 47/100 feet. So the last thing we need to do then is to subtract those two numbers in order to find the height of the observation deck itself, and that would be a height which is equal to 52.35 feet. Let's try an application of a navigation problem. We have the Coast Guard cutter Angelica travels at 30 knots from its home port at Corpus Christi on a course of 95 degrees for 2 hours, and then changes to a course of 185 degrees for 2 hours. Find the distance and the bearing from Corpus Christi port to the cutter Angelica. Let's start by looking at a diagram of what's happening here. So we have Corpus Christi, the port right here, and the ship leaves on a bearing of 95 degrees, and we measure that from north. So that's this right here. Okay, it travels for 2 hours, and then reaching this point, it then goes on a bearing of 185 degrees, again, which is measured from north. In terms of, and it goes for 2 hours there as well. Now, we were told it was traveling at 30 knots. 30 knots means 30 nautical miles per hour. And therefore, we can say that this side is 60 nautical miles. And we can say that this side will also be 60 nautical miles. Well, what we're interested in finding then is this distance, which I'm going to do as a red dotted line. Well, that's obviously a triangle, which I will outline now in green, where we know the two sides. So what we're interested in is what's this angle here? Well, if we look at the two angles they gave us, and I'm going to erase this board so that we can see it more clearly. We know this is 60, so I'll keep that information, and we know this is 60. Okay, so how do we find out this angle? Well, let's look at it in terms of the fact that this was 95 degrees from north. Okay, well, if we then extend this line out, we know that this is 95 degrees from north. Okay, how does that help us? Well, it helps us because we can now measure this angle here and figure out that it's 90 because they must add up to 185 degrees. What that means is the angle inside here is also 90 degrees. All right, so what we now have is a triangle, and let me erase that and redraw it. We now have a right triangle. Both sides are 60. That means each of these angles, because it's a right isosceles triangle, each one is 45 degrees. Now, there are many ways to approach this, and one of the approaches is, since it's a right isosceles triangle, we know that the ratio of the sides is 1 square root of 2, this side being the square root of 2. But we have to multiply each one by 60, so it's 60 times the square root of 2. Well, if we work that out, that would be 84.85 nautical miles. The second part was to find the bearing, so let's do that now. What we'll do is redraw the direction, and what we're looking for is this total bearing from Corpus Christi, which is right here. Well, remember, we knew that this is we figured out that that was a 90-degree angle, and that each of these angles is 45. And therefore, the bearing is simply a sum of 95 degrees plus 45 degrees, or in other words, 140 degrees. All righty, well, next what we're going to do is investigate harmonic motion. Because of the periodic nature of the sine and cosine functions, they are helpful in describing the motion of objects that oscillate, vibrate, or rotate. Let's take a look at simple harmonic motion. A point moving on a number line is in simple harmonic motion if its directed distance d from the origin is given by either d equals a sine omega t or d equals a cosine omega t, where a and omega are real numbers and omega is greater than 0. The motion has frequency omega divided by 2 pi, which is the number of oscillations per unit time. Well, I think the best way to see this would be to work an example and make some sense of these formulas. So here we go. A mass oscillating up and down on the bottom of a spring, assuming perfect elasticity and no friction or air resistance, can be modeled as harmonic motion. If the weight is displaced a maximum of 5 centimeters, find the modeling equation if it takes 2 seconds to complete one cycle, as in this diagram. So here we see that it's going to start at 0 centimeters, and then we will pull it down to 5 centimeters to begin its oscillation. And of course, then it will initially oscillate back up to 5 centimeters, and then it would keep going up and down for a certain amount of time. Well, we assume that the spring started at the origin 0. And the reason that's important is that would be t equals 0, and it would be good to choose the equation d equals a times sine omega t. And because the maximum displacement is 5 centimeters, we would conclude that the amplitude for that equation would be 5. So let me go to a screen, and what we're going to have is d equals a times sine omega t, and we just got through saying that the amplitude would be 5, so it's d equals 5 sine omega t. Then we know that the frequency is omega over 2 pi. And we know that the frequency is 1/2 because it's the reciprocal of the 2 that we were told it takes for a cycle. So now when we solve for omega, omega is 2 pi times 1/2, or in other words, omega is pi. So putting it all together, our equation would look like this. D is equal to 5 sine of pi times t. Well, now it's time for you to try a problem similar to the one we just did. A mass on a spring oscillates back and forth and completes one cycle in 1/2 of a second. Its maximum displacement is 3 centimeters. Write an equation that models this motion as shown on the next slide. So here's the original problem, one cycle in 1/2 a second. The maximum displacement is 3 centimeters, and I want you to write an equation, and there's the picture or the diagram that goes along with it. Now pause the video to work on this problem, and when you're finished, restart the video to check your solution. Welcome back. Let's find out how you did. Now in this example, you'll notice that the string is already stretched at the time t equals 0. So in this case, we would want to choose the equation that d is equal to cosine omega t. So let's write that down. D equals a times cosine omega t. Now, in terms of the maximum displacement, it's 3 centimeters. That means the amplitude is 3. That gives me d equals 3 cosine omega t. We know that it takes 1/2 of a second to complete one cycle, so therefore we'll conclude that the period is 1/2, and the frequency is therefore 2. So that means omega over 2 pi is equal to 2. And that means that omega is equal to 4 pi, and that gives us an equation that models this particular scenario, that d is equal to 3 cosine 4 pi t. Well, great job on that. Today's lesson, we explored using trigonometry to solve application problems, as well as simple harmonic motion. Be sure to work the exercises that your teacher assigns, and we'll see you next time.